Hello and welcome to the second part in the Reigate Maths video on the modulus function from the A-level maths syllabus. My name's Simon, and in this video we're going to be looking at how to solve equations and inequalities that involve modulus functions. In the first video we introduced modulus functions, what they were, and we looked at how to draw some graphs. So if you haven't watched that yet, it'd be a really good idea to stop this video, go and have a watch of that one, and then come back. What we're going to be looking at today is solving equations. So to start off, we're going to look at this basic example here. This is the graph that we drew at the end of the last video, the graph of y equals modulus of 3x minus 2. Solving an equation is the same as finding the point of intersection of two graphs. So this is the graph of y equals the modulus of 3x minus 2 and the graph of y equals 1. We can see here that we have 2 points of intersection between these two graphs. So we need to be able to find them. As we said at the end of the last video, this branch here is the graph of y equals 3x minus 2. So to find this first point of intersection here, we need to do 3x minus 2, this equation, equals 1. And then we solve that normally. But how do we find the second one? Well, again, as we said in the last video, this branch here is the graph of minus 3x plus 2, which we can see is taking everything inside the modulus and changing the sign. So we are solving this equation as well. Now you don't need to write it with the brackets and the minus on the outside. I'm just doing that to demonstrate what's going on. I would start writing it like this and then solving from there. We can solve normally and we get x is a third. We can see we have two solutions. You've really got to pay attention to whether these solutions work with your graph. Now, because we're solving it equal to 1, it's fine. It's a flat line, it definitely crosses twice. But as soon as we start putting this line on an angle, making it a different function, it becomes a little bit more difficult. So we're going to have a look at a second example that is a little bit more tricky and has more variables in. Now here's our second more complicated example. Now quite often in an exam they would get you to draw the modulus graph first if solving the equation is going to be problematic. Now we know this one is going to potentially cause us some problems because if we look at the gradients of the graphs, the gradient of the modulus graph is 1. The gradient of the not modulus x graph is also 1. This is going to potentially cause us problems because we're not necessarily going to have 2 points of intersection. And in this case, we don't. Some equations will, some equations won't. Without sketching the graph, it's quite difficult to see which one it's going to be right from the start, other than looking at the gradients. So let's work through this one and let's see how we get one solution. So following the method that we just looked at, we're going to make the modulus bit positive and solve that equation. So we're going to get the equation x plus 1 minus 2 equals x. The 2, or the minus 2, isn't inside a modulus, so it doesn't need to worry about the sign. Let's go through solving this one. And hopefully you can already see we've got an issue. The minus 1 equals 0. We know this is not true. What does that mean? Well, it means this bit doesn't give us a solution. So let's try the other bit, where we make the modulus stuff, we change all the sign. This should hopefully already be a lot more comfortable. Minus x minus 3 equals x. 2x is minus 3. X is minus 3 over 2. This gives us a solution. This one doesn't. Which means that this equation only has one solution. If we draw the graphs of these, we can see that. So you can see here I've now drawn these two graphs, and we can see that because the gradient of this and the gradient of this one match, there's only one point of intersection, which is here, and that is where we make the modulus stuff minus. If we change the gradient of this to make it bigger, then there would be more points of intersection. If we made the gradient of this less, then there would also be more points of intersection. And we can, if we see here, there we go. So if I make the gradient of this line smaller, like that for instance, we can see we now get 2 more points of intersection. Okay, we get one here and we get one here. So you do have to be careful, but usually if this is something that happens in the exam, they will tell you, or they will get you to draw one of the graphs first. What we're going to look at now is how to solve inequalities that involve modulus functions. And this is our example here. Relatively simple one. Solving modulus of 2x minus 1 is less than x. Now, with modulus functions, as with quadratic inequalities that you did in the first year, it's really important that you draw the graph, or at least have a little bit of a sketch, so you can see what's going on. Now, I'm not going to do this nicely using the straight line functions from here. I'm just going to do it very quickly so we get an idea of what's going on. Because unless you're told to, the graph doesn't get you any marks. It's useful though, because it means that you are able to look at your equations, look at your answers, and solve them. So if we sketch 2x minus 1, but modulus, we can see it's going across the x-axis when y is 0 at a half. It's going to cross the y-axis at 1. So it's going to look something like this-ish. Y equals x is going to do that-ish. Again, my graph isn't perfect. You see I've got a little bit of a horrible thing going here, but that's okay. Now we split our graph, we can see that we have 2 points of intersection. So we want the bit where our modulus graph is below our not modulus graph, which is in between this set of x's here. So we need to work out those x values. And the way we do that is by pretending that this inequality sign is in fact an equals. So we're going to consider modulus 2x minus 1 is equal to x. And this is going to find those points of intersection. It's not going to solve the inequality for us. We've got to use our heads for that. But it's going to find the values of x where change happens. We can solve these equations here. This one comes out nicely. We get x equals 1. Just very simple rearranging. And this one we get 3x equals 1. So x is a third. So this is a third. This is 1. We can see, again, the region where our modulus graph, this one, is below our x graph, this one, is here. It's this region. So we want, so we want our x value to be between 1 and a third. Writing this in set notation, lots of different ways. We could less than 1. This absolutely could be something you're required to do, but this would be an appropriate answer. What students do wrong with this is try and solve the whole thing with an inequality sign, and then they get in a bit of a muddle here. It's really important that you pretend it's an equation, solve it, and then use the graph to work out which region you want, which is this region. Now, the last thing we're going to do in this video is a little bit away from solving equations and inequalities. It's actually going to link with transformations, which are going to be a few videos in the future. And that's how you apply the modulus transformation to graphs. So this is the example we're going to look at here. We've got this function here, x squared minus 3x minus 10, and we're going to sketch those three things. Now the first one is just sketching that graph. So stop the video, sketch the graph, and then we'll come back and we'll have a look at how we can apply the transformations. Okay, so we've got our quadratic graph here. Standard quadratic graph goes through the x-axis at -2 and 5, and the y-axis at -10. So let's have a look at what happens when we modulus the whole thing. So as we've seen in these two videos, the modulus takes a number and makes it positive. What this is doing is we are calculating an answer for this and then applying the modulus function. So we're getting an answer and then making it positive. So here at 5 and -2, the answer is 0. So they're going to be the same. Here at 6, we can see the answer is positive. So that's going to stay the same. But here, for instance, and anywhere in the middle, we can see when x is 0, the answer is -10. So when we get our answer of -10, we then apply the modulus function, and it makes the -10 into a 10. So everything in between these two numbers, the answer becomes positive. Everything outside is going to stay the same. So we get, broadly, the same looking graph outside -2 and 5, but then everything in the middle gets flipped up. Now this is not a particularly nice drawing. I apologize for that. That's a bit better. So there we go. So this is the graph of y equals the modulus of f of x. That's when you take something and modulus the whole thing. This last one here is slightly more difficult. What this is doing is it's taking a number, making it positive, and then putting it into this function so that we get an answer. So if we think about the numbers this side, here x is greater than 0. The modulus function that we're going to apply to an x, because x is positive, it keeps all the numbers the same. So when x is 1, we do modulus of 1. So when x is 1, we get the modulus of 1 is 1. So f of the modulus of x is the same as f of 1, which in this case is minus 12. One minus 3 minus 10 minus 12. Okay, and we can see that when x is 1, that gives us minus 12 here. So this bit all stays the same. So when x is a positive number, everything there stays the same shape. It's when x is a minus number that things get a little bit difficult. Let's look, for example, when x is minus 1. Well, modulus of x is 1. So f of the modulus of x is going to be the same as f of 1, which is 12, minus 12. Well, hang on a minute. If x is minus 2, modulus of x is 2, so f of the modulus of x is the same as f of 2, which is going to be sort of here-ish. F of minus 3 is going to be the same as f of 3. Minus 4, minus 5, and so on are going to be all the same. So we actually get the same shape as this. Oops, let's try that again. The same shape as this, reflected. And this is why doing graphs in pencil is important. That'll do. So this is y equals the f of the modulus of x. So with this one, modulus on the outside, you take everything that's below the axis and reflect it up. Modulus on the inside, the right-hand side of the y-axis stays the same, and we copy it over to the left-hand side. We'll revisit this idea again when we look at transformations later on in the year, or in later videos. So don't worry if you can't quite get your head around it yet. It is a difficult concept. It's not strictly speaking specified on the spec, but the exam board have said that it could be something you need to do. Otherwise, that's modulus functions done across the last 2 videos. Thank you for watching, and hopefully that was useful.